One coming in. Okay, you should be able to see my screen in 3, 2, 1 now. Okay. There is a request for me to share my slide. However, I has yet to share the slide because what happened is that this is a PowerPoint slide and I've made it animation. So to convert it into PDF, some of the things might not appear. So let me convert this into a video tutorial and later well and later I will share this slide to you guys as well. So attendance, yeah, please fill up the attendance, number 1. Number 2, I had just looked into the Jamboard just now, and there are only few of you who had filled this up, but anyway, you can do it sometime today or after class, it's fine. But let me walk through a bit on just to put some comments. Okay, the question here is actually to design a 2-bit adder using only half adders. Okay, one answer from here, Afiq, which is correct. And secondly, this one, I was actually zooming for this answer just now and I saw there is an OR gate. So this is correct as well, but this is not accurate. Why? Because this is how we convert from half adder. How we make a half adder to become a full adder. So if I were to package this as a whole unit, this is actually a full adder whereby it can cater 3 inputs, A, B, the addend and also the outgand, apa ke nama dia, penambah, and the numbers that you want to add, these 2 numbers, as well as carry in. And the output will come from sum and also carry out. Tapi note here, only with half adders, meaning to say how can you cater this by using only half adder. So one of the way is by having half adder to be added at this point. So one tips if you want to solve this kind of questions, okay, ni ada jawapan lain. Okay, now if you want to answer this kind of question, it might be easy for you to get and to see the flow by having this mathematical addition, mathematical process and so on. Okay, there is hilang pula. Tadi there is this one answers coming in, but tak ada lagi kat sini. Tak, never mind. You can keep doing this. I will have a look on this as well. Okay, for those who just come in, let me copy and paste again the attendance and also the Jamboard in case you, Allah Akbar. Tengok in my screen it does not appear, tapi in the screen being displayed here is appearing. Okay, so for those who has yet to fill up the registration form, attendance form, please do so. In the meantime, let's have a look on what are your responses about what have you learned in previous class. So I'm doing this LIFO, last in first out. So in the previous class you had learned about half adder, full adder. Is that all? PLA, PAL, PLD's class intro. Is that all? So I believe this one is in the 2 classes before. Yeah, how about the previous class, the class before this class? We had actually touched 3 things, 3 things. There are more than just half adder and full adder. We had also seen on ripple carry adder situation as well as carry look ahead adder. Okay, the only thing is that I did not go through step by step on carry look ahead adder. Alright, okay, what would you like to learn today? Okay, this one I'm going to use the same method, last in first out as well. You would like to know more about carry look ahead adder. Okay, ripple adder, 2 3-bit adder, carry look ahead adder. Okay. Okay, is that all? You would like to look lagi on PLA, PL? Or this one is the previous class, in the previous class. Okay, all right. So basically, from the responses that were given here, not much. I believe the one before this is related into previous class. Okay, for today's response, I believe they are around less than 20. So the rest of you guys who have yet to fill this up, please do so, yeah. Okay, let me see how much of you guys yang dah fill up today. Today is 24th. There are only 10 of you who had fill up today. Okay, please fill up the attendance, yeah. Okay, and answer this question. Now, the last time, we had seen, mana mouse? Wait, yeah, I cannot see my mouse, my cursor. Okay, here. Okay,
Madam,
yeah.
attendance tu dia sama je atau ada yang ikut minggu lain, minggu-minggu? Ke sama je?
Link attendance tu sama. The attendance link is the same, but I would expect you to fill up the session differently. Okay, macam ni. When you go to the attendance list kan, ada sini, dekat sini, dia akan tanya today's class ni. So today's class ni fill up according to the real time lah. So kalau hari ni the class is on the 24th March 2022. Your responses for number 1 and number 2 would also be different thing. Okay, this first one, I would like to know what did you get from previous class. Kalau for today, I would like to know what have you learned on Tuesday, last Tuesday, and what would you like to learn today. Now, this is actually to look whether if there is any of you who had read in advance and would like to know things that I think I can mention ataupun can cover during the class. Okay, the link is the same, tapi these 3 responses should be different. Okay.
Okay, madam.
Okay.
Thank you, madam.
Thank you. Alright. So, half adder, full adder, by now, dah lagi nak kami in sorry. Okay. Half adder, full adder, two of the basic construction of adder. And ripple carry adder, we had seen how it is being applied. But it seems like maybe you would require further explanation on ripple carry adder as well as carry load head adder. My aim for today's class is to cover the multiplier as well as the ALU. Okay, let us revisit about this adder process. Yeah? So this is adder, half adder and full adder. Now, when you arrange your full adder to satisfy X bit addition, okay, when you have a half adder ataupun a full adder macam ni okay, let's say you have a half adder ataupun a full adder, you can only cater 1 bit process per time. Of course, kalau half adder you only cater 2 inputs, whereby these 2 input only cater 1 bit per time. When you have a full adder, you will address 3 input at one time, whereby you can have A, B. For full adder, you would have A, B, C in. And of course, in both cases, you would have your sum and also your C out. Okay. When you want to do addition can comes from the process you do addition and so on would very much depends on number of bits which the number is representing. Okay, say in one exercise that we did, if we were to add only 1 bit number, so it will be like A plus B, and you will get your summation apa, whether there is or not C out. Okay, kenapa I use the word whether there is or not C out? If A is 1, B is 0, for example, you will only have sum, you wouldn't have C out. Okay. But there are also cases whereby the addition numbers of binary would require more than 1 bit. Okay. For example, in this case, the question is to add in 32-bit ataupun to do the process that involve 32-bit numbers. Okay. If I have, let's say, for example, in decimal, number 9. Okay, I want to do calculation that involve number 9. How many bits would I have to represent number 9? Berapa bit?
Lapan.
4 bit.
Okay, I heard one answer as 8, one answer as 4. Okay, when I talk about bit, mean what kind of representation of number am I referring to? Is it binary system? Is it decimal system? Is it hexadecimal system? When I talk about bit.
Binary.
Binary. Binary ya. Binary.
Okay.
So bila sebut binary ni, when I talk about 9 and when I ask the question just now, how many bits is represented by 9, the thing that you need to do is that to convert 9 in decimal to binary number. So 9 just now in binary, what is the representation of 9 in binary?
1001.
1001, which is the correct answer just now, which is 4. Okay. I am not so sure how 8 is being derived. Tapi this 4. Okay. Now, 9, if you were to represent in binary, means it requires at least 4 bit. Okay. But of course, if I have a 4-bit system, what is the minimum numbers that I can represent with 4-bit system? Minimum number that can be represented by 4-bit binary number.
Minimum.
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 Kalau
1.
minimum means 1 ke?
What? 0.
0. Thank you. Kalau minimum means when I talk about 4 bits means there will be 4 spaces to be filled up. Angka. Sekejap nak recall dalam matematik kita panggil apa? Digit lah. Okay, 4 bit ni kalau dalam kalau biasa when we talk about 4 digit numbers and so on, if we were to talk in decimal representation, makna ribu lah, rumah ribu Okay, tapi in this case 4 bit, the minimum number that I can represent, minimum value that I can represent is 0000, which is equal to 0. What is the maximum value that I can represent with a 4-bit binary number?
15.
15. Thank you. How did you get 15? Is by replacing the 4 rumah 4 rumah dekat sini, the 4 spaces here with 1 1 1 1. So I can add ataupun I can do mathematical process up until number 15. 0 until 15. Okay, jadi when I have a 4-bit adders, for example, when we talk about 4-bit adders, okay, now I'm talking about 4-bit adders, I can add a number. A ni can be represented with 4 binary bit. Okay, the normal notation that we normally use is this one, A0, A1, A2, A3. Okay, so B0, B1, B2, and B3. Okay, so if I were to have a 4-bit number, means I can do addition for numbers between 0 up until 15. You guys are okay with this, yeah? Okay. Means A ni sometimes it can be between number 0 sampai 15. For example, the first exercise that I want to do maybe like 8 plus dengan 13 ke. 8 plus dengan 12 ke, or something like that lah. So kalau example yang kita tengok semalam ni, the example that we seen yesterday with this 5-bit representation. So whenever you have more than 1 bit addition, okay, one of the way to execute is by having this kind of arrangement, whereby we can arrange full adder in such a way. Means to add the first LSB, least significant bit, the first column of addition, we can use full adder not, and then full adder number 1, full adder 2, 3, and so on, depending on the number of bit that is being required. When you arrange in such a way, if you arrange in such a way, this arrangement is called ripple carry adder. Okay, so in previous class, not only you look into half adder and full adder. Half adder means without the carry in, full adder with carry in. But we had also see how can we arrange these adders to become ripple carry adder. Now, kenapa? Why do it being called ripple? Is because carry out of the first process is being taken to be carry in for the second addition and so on. Okay, so this effect ni is known as rippling effect. Okay, but even though the good thing is that it is quite easy. That being said, it is quite easy because if let's say you would need to execute this 4-bit adder, means you need to have at least 4-bit full adder. 4-bit means you need to have at least 4 units of full adders. Okay. It can also be executed by 3 full adder, 1 half adder. Okay, kenapa? Why is that so? Because the least significant bit, the least significant bit here does not require any carry in. Hence, it can be executed by only using half adder because it does not require any carry in. Okay, so that's the case here. However, this simple execution comes with a restriction ataupun with a drawback, whereby the more number of bits that you want to entertain ataupun that you want to do would require ataupun would incur such a big rippling effect. Such being mentioned here lah. If you have 32-bit adders, it requires at least 31 cycle. Why is that so? Because ni, yang bulat-bulat ni, the rectangle that I had illustrate here, represent 1 cycle. So look at this one. You have 5 bits kan? It would require at least 1 cycle, 2 cycle, 3 cycle, 4 cycle, 5 cycle, and so on. Okay. So, okay. Okay, so how do people tackle this, ataupun how do we eliminate ataupun reduce this, is by using this prediction, whereby we call this as look ahead. Why is it look ahead? Because there is this prediction of what can happen ataupun what should happen. Okay, now the concept here is like this, yeah. If let's say you have 1 plus 0, there will always the carry out here, there will always be no carry out, and the sum will always be 1. Okay, kalau you have like 0 plus 1 will be the same thing. And when you have 0 and 0, carry out here can be categorized as none, no carry out that is happening, except if the addition involve 1 and 1. Okay, because 1 and 1 means your sum is 0 but your carry out is 1. So with this scenario and with this notation, with this situation with the carry out case, at the second stage, okay, 1 here, if it is the first stage, I here will become 0. So the next is C1. Okay, comes into second stage. Okay, ni I plus 1 ni, kenapa ada I plus 1 is this one, ya. This is current state, current cycle. So when it has plus 1 ni, means it is referring to the next cycle. So the next cycle of the carry out would involve x dot y, current x dot y. So current x dot y ni is this item. Okay, note here, if I were to execute this one, which gate is representing this x dot y ni? Is it OR gate or AND gate? AND gate, yeah. Okay, kenapa AND gate? You look at here. Okay, let's say this is the number x that you want to add. This is the number y. C out will only corresponds when both are 1, 1. When both are true, then only C out will become true. So the prediction is that if the next ataupun the next carry in would become true when both situation are 1. Hence, AND gate is being used here. Okay, so then x1 or XOR y1, current of x and current of y, exclusive OR, multiply by carry in. So when we do this at first stage, there is no carry in involved. Okay, when we are dealing with this at the second cycle, okay, look at the second cycle. Coming into the second cycle ni, it would require the input of the carry in. Okay, carry in output ni will become the carry input for the first stage. So it is influenced by carry in, which means that if there is carry in being taken into this stage, okay, kalau ada carry in here, then this carry in would influence the overall result, okay, because such as the one that we see here. If you have 1 plus 1 means it is 2. 2 means C out is 1, sum is 0. However, if there is a carry in, then it will become 3. When 3 means it is 1, 1. So sum is being affected. Right? So there is this one representation ataupun one label that we normally call at this stage, whereby we use this G and P. G means generated. Okay, P means propagated. Okay. Okay, I would require this sekejap, tapi I would want to delete this sekejap. Okay. Now, that being said, if I want to do at the same time, if I want to execute these functions, means I need to predict what will my C in for the first stage be. If I want to do this addition, I must predict what is my C1 at second cycle is. As well as, okay, this will depends on C1 at the first cycle. Okay. If I were to do this at the third cycle, I would have to predict C13 here, which is also dependent on the C12 here, which is also dependent on C1 first cycle here. Okay. So that is why when you do this, okay, ni kalau if you were to do at the fourth cycle, macam tu jugalah. Fourth will depends on the third one, the second one, and then also the first one. So that is why this equation comes in. You see, at the first cycle, we depends only on C1. But when it comes to the second cycle, this is where you predict at the first stage. Okay, come into the third cycle. The third cycle will depend on second cycle, which second cycle comes from the first cycle here, and first cycle is this item. G out, G generated, P propagated, yeah? And then it will go through and it will keep evolving, it will keep increasing. So this, if we were to translate it into digital circuit, it can be represented as a combination of an AND gate, 2 input AND gate, as well as an OR gate. Okay? Now, coming into the second stage here, okay, we need to predict this input which comes from this combination of 2 AND gate and 1 OR gate. Yes, I hear.
Madam, sorry
yeah.
madam.
Yes.
Jadi kalau macam contoh, ada soalan kalau dia suruh lukis, ada banyak lukis lah.
Betul. It will depend on how many number of bits yang dia require you to do. Bukan you to lukis atau you to execute. Okay, kalau ripple carry adder, if let's say ripple carry adder, it asks you to do this. Macam soalan yang kita buat tadi, yang kita buat semalam Okay, yesterday's question was to execute this 2-bit adder using half adder. Question can come in such as construct a 2-bit ripple carry look ahead adder. 2-bit carry look ahead adder. So if the question comes in such a way, meaning that 2-bit means at least you need to have 2 full adders. Okay, 2 full adders, if you were to arrange such a way, means you are building or you are designing 2-bit ripple carry adder. Tapi kalau soalan specifically require for ripple carry adder, minta maaf. Kalau the question specifically ask for carry look ahead, 2-bit carry look ahead adder. Now, carry look ahead adder ni macam ni. Dia punya mouse ni hilang. Macam mana nak besarkan? Subhanallah. Saya tak nampak saya punya mouse ni. Bila dia dekat bawah ni dia ada, tapi dia ni atas dia tak ada. Okay. If you were asked to design CLA ni nama pendek, this is a short form for carry look ahead adder. If you were to ask to design a carry look ahead adder, 2-bit carry look ahead adder, means you should have something like this. You should have a full adder, 2 units of full adder, and at the second stage of full adder ni would require extra circuit, whereby this circuit is used to predict what is the C in, so that you can execute these 2 at the same time. Okay, if you have circuit like this, you could eliminate the process that is involved at this stage. Ni first stage, second stage kan, whereby you need to wait for the second cycle to come in. Okay, so that is what you need to do, and I hope how you can do this is by you will I will convert this, I will share this slide later on after this class. Nanti I will make sure that this is like in a separate slide and so on. Try to derive this. Okay, this is the derivation of the answer and so on. Once you get at this stage, to convert this ataupun to translate it into a circuit, it is just quite simple. Macam ni OR gate, it require OR gate. So this should come from P1 and this item. So P1 and this item. What is this item? This is actually G, generated bit. So kalau dekat dalam ni, it letak as G0. So where does this G come from? G come from this X and Y tadi tu. Okay. So the more number of bits that you need to add, it will incur bigger number ataupun the more number of gates to support, and ataupun OR gates to support. Okay. So ni, this is propagated, this is generated. Alright. So that is all that you need to know in and out for half adder and full adder. So yes. Ya.
Madam, CLA dengan Ripple tu dua-dua ada C-in.
Betul. Okay. What makes it different between CLA dengan PLA? Dengan CLA dengan apa nama tu? CLA dengan RCA, Ripple Carry Adder. Set ya. Okay. What makes it different is the additional circuits that you need to add in. Macam ni. Saya buka macam ni. Ni, you tengok dekat belah sini. You guys can see my circuit Okay. This is the execution of side. Ada 3 orang lagi nak masuk. Okay. Selamat pagi semua yang baru masuk. Okay, so kalau tengok dekat sini, okay, saya buka 3 slide serentak kat sini kan. Okay. This is Ripple Carry Adder versus Carry Look Ahead Adder. Both adder would require full adders. Okay, statement ni semua orang setuju kan? Semua orang dapat kan? Ke tak faham? Faham Okay, macam ni. Saya tengah tunjuk sekarang ni, what I am showing to you guys here is actually the execution of 4-bit adder. Okay, 4-bit adder. Regardless, 4-bit adder ni maksudnya adder yang boleh menambah minimum number is 0 up until maximum number 15. Okay, maknanya dia boleh tambah 0 sampai 15. Kiranya operasi tambah adding operation that I can do is to add numbers between 0, decimal numbers between 0 up until 15. Okay, for both cases, I would have to use adders. Okay, mana adders tu ni? Ni full adder. Ni semua full adder ni. Full adder number 1, number 2, number 3, number 4. Full adder number 1, number 2, number 3, number 4. If I were to execute this only with, to use this only to execute Ripple Carry Adder, I would only just have to do the connection. I need to make sure that my C out is connected to the C in. Okay, takat ni semua orang boleh lagi tak? C out to connect with C in. Sekarang I am building up my Ripple Carry Adder. So far so good?
Okay.
Okay. So, if I were to make it the third addition, the third cycle of bit addition, I would require to make sure that I must make sure my C out at second stage is being connected to C in at the third stage. So there's C out for the third stage to be C in at the fourth stage. Ni cara saya nak kena buat Ripple Carry Adder. I can also execute this one using Carry Look Ahead Adder. Still, saya perlukan full adder to execute. Tetapi this time round, carry out saya ni, the carry out here no longer become carry in at the second stage. Kalau ni tadi, carry out ni become the carry in of the second stage. Tapi sekarang ni, carry out ni tak, saya dah tak perlu ambil peduli for this carry out dah. Kenapa? Sebab carry in, because the carry in at this stage, I am predicting it. Saya ramal. Macam mana? How do I predict it? By looking into the combination that I have at A0 and B0 ni. Okay, sebab kita tengok tadi if I have 0 and 0, if both A0 and B0 is 0 and 0, will there be any carry out here?
No.
No. 0 and 1?
No.
Tak ada juga. 1 and 0?
No.
No. The only case ataupun the only situation that I would have my carry out visible here is when I have 1 and 1. Sebab 1 and 1 ni, my sum here will become kosong, but my carry out here will become 1. So in this case, only I will have my carry out. So dekat sini ni, my carry in here ni, I can predict here siap-siap. Kalau by having this input ni, masukkan dia kepada N. Ni, input yang sama ni saya tarik dia jadi kepada N ni juga. Okay, sebab apa? Yang ni saya masukkan dekat sini. Sebab when both are 01, 10 or 00, output daripada N ni akan dapat kosong. So it wouldn't influence my carry in for the second stage ni. Tapi if both of this one is 1, 1, automatically this one should be 1 as well. Okay? Tu cara to arrange carry look ahead for second bit. Second bit tu maksudnya macam ni. Kita ada A0, A1, A2, A3. Nak tambah B0, B1, B2 and B3. So for addition for the second bit addition ni, for B ni, B1 dengan A1 dekat sini, saya kena tambah C in kan? C in for the second stage, right? So this C in ni, I'm predicting it by having an AND gate located here. So that whatever input yang coming from the previous one ni, dia masuk saja input at this stage, I can predict as well. This is what would this become? 1 ke 0 ke? Then I can execute this. Okay. Now, satu stage tak susah sangat lah. Bowl ni settle. You dah settle this part kan? Okay. Tapi bila masuk dekat, when it comes to the second stage, remember the input over here would rely on the carry out that is coming from here, would also rely on the carry out that is coming from the first addition here. So that is why circuit untuk the second stage dia bertambah. Look at this one ya. So this blue is yang nak masuk tu, tunggulah Zat. The blue ya yang nak masuk dekat sini ni, the blue coming here ni, you will see that there is an increment of gates that are required. Because it has to cater the first 2 bit yang kita kisahkan tadi ni. Dekat A0 and B0, A1 and B1. You need to cater that as well. So if you come to the third stage pun sama juga. It will become much bigger because you need to predict what would it be with this combination of these 4 items. A0, A1, B0, B1. There ada element A0, A1, B0, B1 here. Okay, and then masuk into the fourth stage, macam tu juga, you have to rely on these 3 combination. 6 A0, B0, A1, B1, A2, B2 and so on. Alright? So that is why that is why dekat sini apa yang slide ni bagi tahu is that you require less number of cycle because you can do this in parallel. But what is not shown here is this circuit ni. You ada banyak circuit yang you kena tambah. So your size become bigger. Kalau macam ni, there is no additional circuit. Macam ni saja, cuma you require 8 cycles. Yes, there is a question just now kan? Ya.
Maksudnya madam, saya tak ingat.
Okay.
Kalau maksudnya untuk CLA ni, kita kena apa tu, macam kena CI tambah 1 tadi lah, formula tu. CI tambah 1.
Kalau soalan keluar berkaitan dengan CLA tu, you need to include this. Saya sebagai pemeriksa, I would like to see your additional circuit ni. What are the circuits that you need to add on before your carry in? Okay.
Okay, madam, saya telah tengok.
Ada soalan final tu. Ada satu soalan saya I extract from previous semester. I don't remember whether final ataupun test. Nanti you guys try to do it. Kita will discuss regarding this CLA. Okay, selain daripada tu, is there any other questions? Zikri nanti try buat soalan tu Sama-sama lah dengan lain. Try buat soalan tu, tengok. Okay, how about the rest? Okay? Okay. Saya masuk dulu di multiplier ni. Nanti kan kita buat soalan sama-sama ya. So the 4 things that you need to make sure that you should know to cover this adder is these 4 things ya. These 4 things, they are not different. They do not differ very much between one to another because they are building up all of here is building up from full adder lah. Okay, of course full adder you can use either full adder or half adder depending on where the addition process is. If it does not has any carry in properties, then feel free to use full half adder. If there is carry in and so on, remember you need to use full adder. And ripple carry adder and carry look ahead adder would require full adder. Both require full adder as well. The only thing is that carry look ahead adder would require you to build extra circuit to predict the carry in. Okay, so that is the conclusion for adder. Now, going into multiplier. Okay, ada orang nak coming in lagi. Okay, let's do this. You go to the Jamboard. Okay. Apa hal? Sorry, saya tekan stop presenting. Takkan dia tak ambil effect kan? Okay, go to Jamboard. I want you to do this. Astaghfirullahaladzim, slow. Okay, do this ya. Okay, siapa nak letak boleh letak jawapan tadi tu. Okay, now let's do this for 3 minutes here. Okay, what I want you to do later is to complete a 2-bit multiplication process. Okay, what I meant by this 2-bit multiplication process is something like this. Okay. Dah tunjuk jawapan. Alright, so 2-bit multiplication process means when we talk about 2-bit, remember the number to multiply is always 2 numbers. Okay, 2 numbers ni memang dia 3-bit ke, 1-bit ke, 4-bit or 6-bit and so on would require 2 numbers. What number is represented by number of bit as the one that we discussed just now. But what I want you to do here is that I want you to complete this process. So if you were to do multiplication with 2 bits kan, how do you do that? Okay, for example, A0 and B0, it will be A0 multiplied with B0. Okay, complete this whole thing. Let's do this for 5 minutes.
Madam, soalan madam tadi
Betul. Saya nak you complete this 2-bit multiplication. Saya paste kat dalam ni Sekejap. Saya paste kat dalam. Tak apa paste, saya display saya paste kat dalam, saya paste kat dalam WhatsApp group ya. Okay, I want you to complete this one. And at the same time, I will copy a couple of questions for us to do. So do this dalam 5 minutes, boleh 3 minutes, 5 minutes lagi. Okay. Can you guys do that? Okay. So okay. Okay, ada dua Okay, when we talk about the process kan, okay, why do we do this? Because we want to see what are the input and output involved. Alright. So the first answer that I received this one, okay, this is correct but incomplete. The complete one should be something like your friend show here. It should have the results ataupun the products that you would want it to be. Okay, contohnya when you multiply these two items, then after multiplication you should add it one to another, right? So that addition process and so on ni, better put another variable to represent that lah, such as the one shown here, P1, P2, P3 and P4. Now, keep posting in. Kalau yang you dah buat, keep posting in. I will look at this as well. Okay. This is a they are actually the same thing. What I want to tell you here is that A multiplied by B is equivalent to A and B because of the nature of the gate. Okay, and gate ni, if both are low, then the output will become low. Both are high, only then it will become high. Other than that, it will become low. So it is something similar to what do we call that? Something similar to multiplication process. Okay, so when you have two bit number to multiply between one to another, you would have something like this lah: A naught, B naught, A naught and B naught, A naught and B1. Okay, how do we do here? Same like your mathematics dulu. This first bit multiply by the first bit on top. The first bit as well multiply with the second bit on top. Make sure your positioning is also correct. Sama macam how you do your normal mathematics function and so on. Sekejap, tak ada pula tukar colour. Okay, so if A1 here, okay, row for A1 should be here. So A1 and B0. And this one is A1 and B1. Okay. And then this whole thing, the end product would be the element here plus nothing. Should be nothing here because you are moving this by one step. And then these two add together. If there is any carry out, will become carry in. Then it will be adding this to this element, as well as the reserve in case there are spillover. Okay, spillover ataupun like we had seen in our adder before last week. So kalau if adder, the general rule of thumb is like number bit. Let's say you have A plus by B. If A is 3 bit, B is 3 bit, your sum here will always be 3 bit plus 1. Okay, it need to be at least 4 bit because it need to cater in case there is carry out. Okay, but for multiplication, if let's say A is 2 bit, B is also 2 bit, the general rule of thumb, it should be 2 multiplied by 2. Sum should be at least 4 bit. Okay, so that why it need to be 4 bit? Because this is rationalizing it lah, why it need to be at least 4 bit. Because you see this one, there need to be a shifting process here. So that shifting and so on would require, and at the later stage you would require to add on. So this is always reserved in case there are failovers between this first number. If let's say this is 1 and there is carry out being linked here, then you have no choice, you need to cater this item. So general rule of thumb, it will be something like this. If adder, number of bit here, add number of bit here, then the result, the maximum number, let's say this one kalau this one 4 bit, this one 3 bit, 4 bit add by 1. The maximum bit number add by 1. Kalau it is like multiplication, it should be multiplied between these 2 and 2 bit. That being said, if let's say you have A is 2 bit, B is 3 bits, so sum need to have at least 6 bit. Alright? Why is that so? Because the shifting that is happening here. So how do we implement this circuit? Okay, you can implement this by translating the process into gates. Okay, this one is A naught, B naught. Multiply is equal to AND. So here you can represent ataupun you can have AND function to execute this item. Okay, one element here. The second AND gate to cater this second item, A0 and B1. A0 and B1. So there's this item, A1 B0 and A1 B1. Okay, then you can see here, this element would straight away be the product, the resulting product of P0. Okay, because you wouldn't have anything to add on here. So then it can tarik directly to become product numbers product not. Okay. For product number 1, it should involve the addition between this element and this element. So this is a half adder ke a full adder? Looking at this kan, this is half adder or is this a full adder? How many inputs are there? Only 2 input, right?
Inputs.
So X and Y. So you can execute this using only half adder pun dah boleh, because this coming from a element here and element here. Now, will there be any chance ada carry out as one tak? Here, A0, B0. Tak akan ada because A0 and B0 ni, the product will always be only 1 digit. Okay, if 1 multiply by 1, 1 and 1, it will become 1. Okay, tapi kalau tadi sum tu 1 and 1, it will become 2 because that 2 representing 2 in binary would be 2 bits, 1 and 0. So this one can also be implemented using half adder. So this is resembling this process and this is resembling this process. Now, this process here, this is actually carry out, okay, coming in over here. So that is why you can own using half adder pun dah sufficient. You need not to have full adder. Alright? Tapi kalau it involve 3 layer, okay, when there are 3 layers means half adder ni has its limitation. If you want to use half adder juga, you need to do something that what we did in the previous exercise. You need to cascade 2 half adder to become 1 full adder. Okay? So that being said, let me walk through how did you guys do. Load pula dah. Ada orang coming in? Tak ada So our class basically 10 AM lah. Right? So if tadi pun kita dah tunggu 10 minit kan. Okay. So mana tadi? I want to see your Jamboard answer. Subhanallah. If is kalau. Okay. Apa hal pula WebGL ni? Okay. Sorry sekejap. Okay. So if it requires more than 2 bit, half adder might not be relevant to do it. Okay, dia ni ada problem pula. Sorry bear with me 1 moment. Okay, tak apa.
Madam, tadi betul madam?
Ha?
Tadi yang betul madam buka tadi betul?
Tak, cuma ada isu. Saya tengok dia ada display. You guys can see my screen kan? Cannot display Jamboard. Enable WebGL. Tahu apa ke benda WebGL ni pula. Saya try buka dengan browser lain. Kalau tak pun tak apa. Kalau tak apa. Nanti kan kita ni. Ada something yang saya tak activate dengan kot. Ni. Okay, saya buka dengan tu. Dengan browser lain. Okay, tak apa. Thank you. Sorry Ni dia ada something, kenapa entah dia tak boleh tunjuk kat saya punya screen. Tak apa, kita guna ni, dah boleh solve. Okay, so yeah, let me have a look. Okay, now your friend give this answer. Okay, now ada error dekat sini sikit. What is the error? What is the error? Okay, is this correct?
Not correct.
Why? Why is it incorrect? Ya Allah. Why is it incorrect? Okay. Remember, when we do mathematics kan, kalau I don't know how to say this in English, tapi kalau in bahasa Melayu, we used to call this as rumah lah, rumah sa, rumah puluh, rumah ratus, rumah ribu. So sa means number up until 10, and then we have tens, number in tens, number in hundreds, okay, number in thousands and so on. So why is this wrong? You need to shift this one. Apa dia ni kak? You need to shift this one. Tak boleh komen ke ni? Boleh kan? Okay. You need to shift this element to this state here. Okay. A0, B0 correct. A0, B1 correct. Okay. The second tier, when you want to do A1, B0, it should be here. A1, B0. And secondly, A1, B1 should be here. A1, B1. Okay. Then only you will have your product number kosong, product number 1, product number 2, product 2, and so on. Okay, the element here is correct, cuma the positioning is incorrect. Okay, so the results of the multiplication is incorrect. Okay, let us see others. Allah. Oh, dia ni tambah kat page depan. Okay, kejap. Okay, so tadi, how you did is, this is correct. Okay, yang ni, the elements here are correct, but the product here tak ada. Now, why it is important for me to see that you have the product as well is because if you don't note there is P0, P1, P2, P3, and P4, there is a tendency you miss out the operation that you need to add here. P ni maybe directly, but here you need to add adder. Okay, now adder in this case, half adder saja dah cukup. Okay, tapi kalau dia involve more number of bits, half adder maybe is insufficient. Okay. Yeah, your friend here noted here, this one is the addition process and so on. Okay. Okay, yang ni pun sama betul. Okay. Now, it comes into a situation whereby, what if we require to do more than 2 bit? Okay, such as the one that is being shown here. If let's say we need to have up until 4 bits multiplication kan? Ya, saya buang ni yang lama ni. Okay, let's say in this process, 4-bit multiplication, similar like the 2 bits just now, what you need to make sure to do is to do this first stage, buat sampai habis, it will be into this tier. When you do the B1, it will be into the second tier. First tier, third tier, first, second, third, fourth tiers ni, make sure they shift by 1 bit position. Don't make it a line. Okay, because if you were to make it a line, your representation of numbers here and also the tens representation, bukan tens, the position wouldn't be correct. Now, this is actually the same as the mathematics that you did with decimal number. So if let's say decimal number, you have number in, kalau BM we call this in English, I'm so sorry, I forgot what it is being called. The second one, we call this in tens. The third one, we call this in 100. The fourth one, we call this in thousands. So if you have like 3, 2, 1, 5. Now, if this number, the same number you were to write something like this. So these two numbers here, even though it involves same numbers same numbers, but the value are different. Okay, because the position of this housing this house. So that's when you do so the implication is also the same when we do for binary, meaning to say make sure that you do this shifting and so on. Okay. So if in this 2-bit addition, we can execute this using half adder, okay, like the one that we show here. But when it involves more than 2-bit addition, such as the one shown in our third column here, whereby you have 3 elements to do, half adder sahaja might not be sufficient. Okay, the one that we have here, 1 full adder pun is insufficient because you have 3 bits to add, and remember there is also 1 carry out. Okay, kenapa we require this full adder and also half adder? Because there is 1 carry out here. If it is 0 and 1, no issue. 1 and 0, no issue. But if it is 1, 1, you would have two numbers here. 0 and 1, which will become carry in at the third column. So to cater that, you require full adder to add these two items, and you require another half adder to add in these two as well as this this carry out just now. Okay, so when it goes to the fourth column here, fourth column would require 1, 2, 3, 4 bits. 4 bits element to be added. Okay, full adder kalau ikut 4 bit full adder ni it has 3 inputs, isn't it? So kenapa, why do you need up until 2 full adder, whereby if you have 1 full adder and 1 half adder, so half adder ni you have like 2 bit input, this one you have like 3 bit input. Okay, banyak-banyak hari ni ada kapal terbang nak lalu. Okay, I am in Pekan by the way, UMP Pekan. So if you have this one, it should cater sufficient input, isn't it? Three inputs and 2 inputs. 5 bits, 5 inputs you can cater. Whereas here you have only 4 inputs. But why do you require more numbers of full adder and half adder? Because of the spillover that may incur. Okay, spillover tu macam the one that I mentioned just now. When you have 1 and 1 ni, you would have 1, 0. You have this 1 bit spill. Okay, this 1 bit spill ni you need to cater. So that is why, even though there are only 4 bits to add here, it requires at least 2 full adder and 1 half adder. Okay, the peak is here. Why? Because the next column, only 3 elements are involved. The fifth column, 2 elements. The sixth column, only 1 element. Okay, and that being said, why do we need S7? Because addition from here ni there is a tendency for spillover. Hence, you need to have one proper placing for this element. Okay, so it goes back to the general rule of thumb as we discussed before. If A is 4 bit, B is also 4 bit, so the total number of bits here should be at least 8 bits. 8 bit ni S0 up until S7 lah. Okay, I mentioned just now multiplication kan? Sebenarnya addition. I'm so sorry addition. So kalau dekat sini A 3 bit, dekat sini pula A, katakanlah B you have 2 bits. B here 2 bit. So this one at least you need to have 5 bits. Bukan multiplication addition. I'm so sorry tadi I used the word multiplication. It is addition. So sum here need to have at least 5 bit. Okay? Ada soalan tak?
Madam, yang contoh tadi tu sama lah.
Contoh yang mana tu?
Yang madam bagi tu, multiplier yang soalan pertama ni.
Soalan ni ke? Sekejap. Mana tadi?
Yang madam dekat Jamboard tu.
Okay. Dekat Jamboard ni, dekat Jamboard ni saya letakkan this one ya. Saya letak you to complete a 2-bit multiplication process. So ini jawapan yang tepat. Okay, bila dia mention 2-bit multiplication process ni, must ada product yang keluar dekat sini, dan this number of product ni must be correct. Okay, tak mau setakat P2 saja, kena ada P3 because there are tendency untuk nak ada lebih. Okay, input ni bila dia kata 2 bit ni, kita akan periksa I need the schema will always have something like this. 2 bits means the first number require 2 bit, the second number pun require 2 bit. Okay, kalau dia cakap proses saja, you tunjuk matematik ni saja dah cukup. Kalau dia cakap design a circuit, design a 2-bit multiplication ataupun multiplier, jawapan need to have something like this. I would expect to see some gates involved. Something like this. Okay?
Madam, yang truth table tu perlu ke?
Truth table tak. Truth table ni tak perlu. Truth table ni sebagai reference saja. Okay.
Madam, yang darab tadi, yang Jamboard tadi tu, Madam buka yang Jamboard tadi ni.
Yang Jamboard tadi, okay.
Yang PO1, PO yang PO1 tu kena darab lah. Kena tambah lah tu. Ni.
Ni. Okay. Okay, saya buat dekat sini
Saya
Dekat Jamboard tu dia susah nak conteng. Okay, saya buat kat sini. Tak apa. Sekejap ya. Okay, saya guna blackboard saya. Okay. Ni okay. Ada, okay, kita ambil contoh lain Let's do ni, I have like this one. Number B ni, saya nak execute ni lah. Okay. I want to execute 3 darab dengan 4. Okay. So, when I talk about this, I want to do a circuit that would be able to execute this function, 3 multiplied by 4. Okay, how many bits do I require to represent number 3? How many bits do I require?
2 bit.
2 bits. How many? The question is how many bits do I require to represent number 3? So another way of asking it, in binary, what does 3 is? What is 3 in binary? So 3 is 1, 1. So I require 2 bit. How many bits do I require to execute number 4? Value 4.
3
bit. In binary, 4 is 100. So if let's say this kind of thing appear kan, this kind of thing being asked, okay, means first, okay, I label this one as my A number, this one as my B number. So for A, I have 3 bit. So I would have A kosong, 2 bits, sorry, A kosong, A1. Okay, B pula ada berapa?
Ada 3.
3 bit. Kenapa 3 bit? Because number 4 tu I cannot represent with only 2 bits. I require at least 3 bit. Okay, sampai setakat ni? Okay? So this is the multiplication process. So let's execute this first one ya. Tolak tepi. Okay. So the first process to be here, apa dia? A0 and B0. Ni kan? Second?
A1, B0.
A1, B0. Okay. I had processed this for B0. Okay. Now I'm moving into B1. For B1, I should start beneath B1. Should not start here. So this one should be B1, A1.
A0.
A1, A0. Remember, dia kena darab from the least significant bit. The second one should be A1, B1. Okay, selesai dah ke? Have I finished doing this?
Yeah.
Not yet because I haven't done for B2. So for B2, where should I start? Here. Okay, B2 ni bawah kat sini So B2. So the first one should be B0, B0, sorry, B2 B2A.
B2. A0.
A0. Ni B2 ni. Okay. The second one should be B2A, A1. Okay. So bila dah selesai dekat sini, so this element will become your product number 0. This is product 1, this is product 2, this is product 3. Sampai setakat ni okey?
Madam nak tanya. Yang produk tu kan dia just nak tulis huruf P ke kan tak ada sum kan?
Boleh.
Itu cara tulisan je lah.
Betul. Tu variable je. Suka hati you nak buat apa pun boleh. Dia variable. Nak guna P pun boleh, nak guna S pun boleh. Dalam contoh-contoh in the previous example, the one that involve addition, I put it as S, just nak bagi tahu dia sum. So yang ni produk ni we put as P. Tapi kalau tak berkenan S dengan P, nak buat X, M, N, any alphabet should be fine. It is just a variable. Okay. If let's say in this case kan, is this complete? Ada saya termiss apa lagi tak?
Tak ada.
Tak ada? Tak ada dua-dua? Satu tak ada, dua tak ada. Betul ke tak ada? Remember tadi, apa tips? What is the tips that I mentioned just now? How many number of product ataupun how many number of sums is required? How do you estimate?
7.
7, 2,
3 plus
2
7
bit dengan 3 bit here kan. So in total your product should be how many elements? Ingat tadi tak? Kalau your 5. How do you determine this? By adding. Kalau this one is 2 bit, this one is 3 bit, so 2 plus 3 is 5. Your P should be at least 5.
5 bit.
5, okay. 5 bit maknanya ni 4 lah sebab saya start pada kosong here. Now, kenapa ada dekat sini? Remember this one ya. There can be a situation whereby this is 1 and there is a carry out daripada sini. Ada carry out coming over here. So this carry out, kalau dia 1, 1 and 1, there will be 1, 0, isn't it? 1 dan 1 akan dapat 2 kan? 2 tu bersamaan dengan 0, 1 dekat sini. So, that is why you need to do up until P4. So, kalau soalan ada tanya this kind of thing for you to derive or for you to show the mathematics process and so on, make sure correct number of P ataupun S, sum lah, correct number of element bits here. This should be resembles by knowing this process lah.
Ma'am, kindly can you repeat this step?
Which
If
the whole
possible.
thing here.
Yes, ma'am.
Okay.
How we determine the? Yeah.
Sorry, how? How do I determine the? Okay, satu set request for one. How about the rest? Are you guys okay?
Okay.
Madam, yang saya madam untuk addition tadi tu memang tu lah apa dia.
Okay, tak apa. Okay, memang tu lah jawapan dia. Okay, okay, let me try this one with numbers kot. So you guys nampak lagi senang kot Okay, tadi saya buat apa? 3 darab 4 3, okay. Now I'm repeating this process Syed, but now I'm using numbers 3 multiplied by 4. So 3 in binary is 1, 1. 4 in binary is
100.
100. Okay. So this one if I were to multiply I am not using shortcut. Kalau using shortcut ni dah tahu dah 20 kat belakang ni, satu kat depan okay, this is the process that involved. When you want to analyze multiplication, same as like in decimal number, 0 multiplied by 1 become
0.
0 here, multiplied by 1 here becomes
0.
0. Here pula 0 multiplied by 1 become 0. Setuju 0 here multiplied by 1 become
0
juga. Okay.
0
0.
1
Okay, 1 multiplied by 1 here becomes
1
1. 1 multiplied by 1 here becomes 1. Okay. Then I do this addition. Kan proses matematik biasa kita buat kosong ke kosong sini. Second stage, what do you need to do? 0 add 0, isn't it? Becomes
Yes,
0. 0 add 1 becomes
1.
1. Okay, nothing carry in out here, so this become 1. So the answer is 1100. So 1100 ni if you were to translate just to cross check is your what you are doing is correct or not, make it 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 is equals to 4, 2 to the power of 3 is equals to 8. So the total is 12. Jadi betul lah dia 12. Okay, this is how it looks like when we were to do this in mathematics. Okay, when we want to do this in binary, in digital circuit, when you want to implement this in circuit, you need to know ataupun you need to get the Boolean expression. So how do we get the Boolean expression? Is by something similar that what we did just now. Okay, this is the repeating of the one that we did just now. I'm labeling this one as A0, A1. Okay, ni Okay, now I'm repeating this one as B0, B1, B2. Why do I have B up until 2 is because I want to represent number 4 which require 4 bits. So the process here, first I need to multiply, isn't it? So dekat sini it should be A0, B0. Secondly, here A1, B0. Okay, I've completed the first task of doing this. B0, A1. Okay, now I'm doing for the second stage for B1 pula. So this one is B1 here with A0. Here and here, it should be A1, B1. Okay, ada is there any problem if you were to do A1, B1 ataupun B1, A1? No problem ya. Because A1 multiply with B1 is similar to B1 multiply with A1. 3 darab 4 sama dengan 4 darab 3. Okay. So, once I had done here, this whole thing here is to cater this B1. Now, I'm looking into B2 pula. B2 with A0, B2 A0 is here. B2 with A1, B2 is with A1 is here. Alright? So,
Okay, ma'am.
altogether, okay. Now, up until this stage, how do you determine the answer? So, 0 is being taken directly out as your sum product here because nothing to be added and so on. So, this can be directly to become a product. Bukan a product. I am representing the whole thing. My answer here is in P. So, this is P bit, the least bit, P0. Okay, how about this one? Okay, for P1, I need to add on these two in order to get here. Remember this one? I add 0 at 0. Kebetulan pula 0, 0, the jawapan is 0. Okay, I have to add 0 and 0 here. And 0 add up to become 0. So, this is add together with this one. And this one also need to be added with these two. A1 and B1 need to be added. And this will become P number 2. And later this is P number 3. Okay, remember this one, in this example, it is 1 here and there is no carry out from this addition. So, you have 4 bits pun is sufficient. Okay, but when you want to do your answer here, you need to put up until P number 4. You need to spare an output for bit, the most significant bit. Okay, because if this is to be multiplied 3 by 4, then there is no issue. But if, let's say, for example, it is like maybe the maximum 3 multiply with 1117, 21, yeah? There is a number being represented by bit number 4 here. So that is why this is you are required to have at least P number 4 here, which is the 5th bit of this product. Okay, up until here, are you guys okay?
Yes, ma'am.
Okay. How about the rest? Are you guys okay?
Okay, madam.
Okay. Now, before we go with the next thing that I want to cover, that is the process of getting the expression. How do you translate this into circuit? Okay. So tadi
Using half adder.
Betul, using half adder ataupun AND gates and so on. Yeah, you are right. So this is the first process. We look into the mathematics process of binary multiplication. The second process, we are actually replacing this with binary representation with Boolean expressions. Okay, the third process is to convert this into circuit. So A0, B0 ni, you use an AND gate pun dah sufficient. Okay, of course you have here A0, A1. Lagi ada pula here B0, B1, B2. Okay. Ni cara orang malas. Kalau you nak nota you buat elok-elok lah. Okay. Sebab mouse ni dia tak accurate lah. Buat cantik pun tak. Okay. Ni A0 masuk ke sini. Your B1 coming here. So this will directly become your product 0. Why is that so? See, my product 0 is coming from A0, B0, and B0. So this is actually A0 and B0. Okay. The second item here, I need to have A1 and B0. So yeah, AND means I will require one AND gate. Where does this comes from? A1, B0. So tarik here from A1, tarik here from B0. Oh, okay, tarik here for B0. Okay, second element is this one. I need to have B1 and AND node. So another AND to cater B1. B1 over here. And another one more is A0. Tarik from this A0 to cover over here. This one come from B1. Yeah? Okay, this item here. So then, these two things needs to be add up together. When it involve adder, you always have two options. You can use full adder or half adder. Okay, but please take note. If it is the first addition process yang you only have two element, half adder pun tak apa. But if it is like that, like this stage, whereby you require a carry in that you need to be careful. So if you were to use a half adder, means one of your input is coming from the first gate here, and the second of the input is coming from the second gate here. Okay, hasil, the resulting, the results here, the resulting element will be in two terms. One is in your sum. Sorry, saya tertekan. Okay, one is in your sum, which your sum here ni will be your product number 1. The other one is in terms of carry out. Okay, your carry out ni should be fed into the third element. Okay, masuk kepada third element ni, there is the third column, the third column here, there is an element that you need to cater for this phase, which can come for X, need to cater for this phase, which can come for Y, and you need to cater this carry in element. Okay, if I were at your shoe, instead of using half adder, I will directly use full adder, because full adder got carry in, whereby you can cater carry in directly. Okay, then this will become your P number 2 from the sum, from the sum output pin. For the carry out ini will pass to the next stage here. So the next stage here should come from B2A1. So B2A1 ni is another AND gate over here. B2A1 masuk. And this should be added up. Okay, dekat sini 2 elements saja that you need to cater. One is the carry out over here, and the other one is the total, is the AND, the product of B1 B2 ni, the product of B2A1. So here I made the option to use a half adder. So one is coming in through its X, one is coming in through its Y, and here there is your P number 3 and also P number 4. So far, are you guys okay?
Yes, ma'am.
Okay. How about the rest? Thank you, Syed. How about the rest?
PO madam tu memang tak ada benda-benda lah.
Apa dia? Ulang balik soalan.
PO. Tak ada, memang tak ada sambung.
Tak ada. PO ni, kenapa? Why there is nothing? Because P here, PO ni, the least significant bit, yang belah kanan sekali, LSB. Dulu masa digital mesti ada pernah jumpa ni, perkataan ni, LSB. Okay, least significant bit. Least significant bit ni comes directly from the product of A0 dot B0. So that is why there is no process required here. Tarik directly saja.
Okay,
Okay.
madam.
Okay. Okay? Okay.
Okay, madam.
Alright. Okay, tak apa. Nanti saya akan share this video recording. Please review that. And kalau require lagi ni, nanti note dekat dalam response survey attendance tu. I will find what are the ways that I can use to explain this. Okay, to execute just now tadi tu, okay, you tengok dekat sini the one that we did, ataupun ni, the one that has been shown here is executing this circuit using gates. Okay, there is also ways of executing this using lookup table. Okay, using lookup table. Now, how can we use this in a lookup table punya form? Okay, remember, kalau lookup table means it is a table after all, right? Betul tak? It is a table after all, kan? So dekat table tu, normally what do we have in a truth table? Lookup table ni is built up from a truth table. So now I'm building up a truth table dulu. What do we have in a truth table normally? We would have
Inputs and outputs.
Oh, okay, good. Thank you. Input and output. Okay. So in this case, the input, what are the inputs here? For this 2-bit multiplier, kan?
A and B.
A and B. How many bits is A? How many bits is B?
1 bit.
2 bits, ya. So dekat sini, for your input column here, you should have, like, let's say this one is A0 and A1. Then you can have B0 as well as B1. Okay. And then the output here, you will see that there is this rule of thumb. If there are 2 bits for element number 1 and also 2 bits for element number 2, so you should have at least P0, P1, P2, P3, at least 4. Okay. That being said, how many inputs that we have all together? If we were to split, tadi we are splitting it into properties. You have A properties and B properties. Now we are talking about bits. How many bits is our input size? If you look through here, A is 2 bit, B is also 2 bits. So altogether, how many bits?
4 bits.
4 bits. Okay, if 4 bits means your truth table ni will be derived from 0, 0, 0 up until 1, 1, 1, 1. Okay, in between ni you guys tahu kan? You guys know, right? From here, then it will be up 0, 0, 0, 1, then later 1, 0, 1, 1, then 1, 0, 0, 1, 1, and so on. Okay ya? Sampai setakat ni okay ya?
Okay, dah.
Okay.
Boleh.
Now, tadi how we do is by executing this. Okay, now what I'm doing is by using this as a lookup table format ataupun truth table. Okay, so how do we determine the output? So let's take the first row here. 0 multiplied by 0. The result is 0 darab 0 is 0. So all are zeros. 0 multiplied by 1 pun 0 juga. So all are zeros. Okay. Let's say you have at this level ni saya pakai tambah this is an example. Ni 01. 11 means 3. 11 means 3. 01 mean 11 here, B 11 is 3. 01 means
0, 1.
So 3 multiplied by 1. What is the result?
3.
3. So here it should be 0, 0, 1, 1.
Yes.
Okay. Katakanlah you come into the last column here. 1, 1 multiply by 1, 1. 3 multiply by 3. Berapa? What is the result of 3 multiply by 3? 3 darab 3 is equals to?
9.
9. So 9 means 1, 0, 0, 1. Okay tak?
Okay, madam.
So, macam ni. Jadi, when you want to execute multiplier ataupun adder and so on, there are ways of doing it. One is by implementing circuit. So, how do we implement circuit? Is by taking this mathematic process and transfer it directly with mathematic gates. Another one more is by using this lookup table or truth table. Okay. Last time when you learn digital electronics kan, once when you had derived your truth table, the next step is to do what? To derive
To
the
design a
Boolean.
circuit.
Sebelum sampai circuit, you had to derive the Boolean expression. How do you get Boolean expression from truth table? What do you need to do normally?
Okay, ma'am.
Maths.
Need tu bukan perkataan lah, you can. Sebab apa need tu bukan perkataan? Okay, why? It is not compulsory to do K-map. Okay, if you don't do K-map, what you would do is that you would extract what is the ones from this output, like the one that we had seen in our class PAL, PLA kan. You can extract that and later use Boolean axiom to get the simplified equation. Why do we need simplified equation? Because we want to use less number of gates and so on. But when we use graphical method, K-map ni is actually a graphical method whereby you transfer this one. So looking at this, how many K-maps do you require? Looking at this combination, how many K-maps do you require? How do you determine number of K-maps? Is by looking into the input ke the output? Good. Jawab kuat sikit. Betul. Jawab betul tu. Cuma kuat sikit. Looking into the output. How many outputs do we have here? 4. So P0 you need to do 1 K-map. P1 you need to do 1 more K-map. P2 1 more K-map. And the size of K-map. What is the size of your K-map? Size 2 means what is the number of cells is your K-map is. is your K-map is. What is the number of cells does your K-map has? 16 lah ya. Sebab dia daripada 000 sampai 111. So, the next step kalau nak buat K-map ni is to take this one column, transfer this into K-map. Tariklah ni combination dia apa. So, ni akan jadi A0, B0, A0, B, A1 ke for example, lawan dengan B0, B1. So, masukkanlah 01, 0, 11 dan loop dia yang mana sepatutnya. Then from there you get the equation. Equation ni maybe akan ada A0, B1, add apa benda begitulah. Then from here you transfer into gates. Okay. So, this is the second way of implementing it. Alright. The third way of doing it by using multiplexer. Okay, sebelum saya masuk ke multiplexer, are you guys okay with the lookup table? Any questions or anything you would like me to repeat? Or do you get it? Okay, sekejap lah. Tengok depan.
Madam boleh repeat untuk lookup table sikit ya?
Okay. Dekat bahagian mana yang you get confused?
Yang akhir-akhir tu. Yang macam nombor satu-satu tu.
Yang macam nombor satu-satu untuk?
Lookup table lah. Yang dapat PO P1 lah, P0, P1, P2. Yang masuk dalam kotak tu.
Okay.
Saya Madam boleh jelas sikit ya? Boleh jelaskan sikit.
Sekejap Saya nak tambah slide tapi tak keluar pula. Okey, sekejap. Okey. Okay, so tadi kita tengok just now we had seen how can we do this directly transfer into circuit. Okay, another one more is by using lookup table ya. So when you want to do lookup table, the first thing that you need to do, you need to derive your table. So how can you derive your table? First of all, we will have one table, and that one table ni we would do input at one side and also output at the other side. Okay. Numbers of input and numbers of output. You have 2-bit multiplication numbers. A0, A1, satu lagi pula B0, B1. So this require 2 bits, this require 2 bits. So the results, the normal way ataupun one is the rule of thumb that we normally use is that we estimate the number of, kalau dalam case ni I'm using P as my product and I want to know what is the size of my product. 2 plus 2 is equals to 4. So my P should be 4 in size. So, ni akan jadi P0, P1, P2, P3. Okay. P4. 4 bit. Tapi saya guna P3. Dekat sini dapat Sebab P ni, I am representing it from P0. P1, P2, P3. Okay. Dia still 4 bit. Tapi dia guna notation sampai 3. So, this is where the product is, and then for input ni, A ni is 2 bit, A0, A1. B is 2 bits as well, so it is P0 and B1. Okay. How do we determine what are the output corresponding to the input? Is by looking into the element that you want to multiply. Now, having this one means you can represent this one 4 variables input, means 0, 0, 0 up until 1, 1, 1, 1. So, if 0 multiply by 0, the answer is 0, isn't it? So, tak ada masalah. 0 means everything is kosong. Means, bukan tak ada masalah. Means it's straightforward. Dia jadi kosong. Okay. Let's say you have, at this stage whereby you have like maybe 1, 0 multiply by 1, 0, for example. 1, 0, what is the number represented by 1, 0?
2.
2. 2 multiply by 2 is equals to?
4.
4. Kalau 4 dalam binary, how do we represent it in binary?
1, 0, 0, 0.
0, 1, 0, 0. 1, 0, 0 tadi jawapan dah betul, but we are talking in terms of 4 bits. Jadi saya letak kosong lah kat sini. 0, 1, 0, 0. Okay, saya ambil pula contoh lain. Katakanlah 1 darab 3. 1 multiply by 3. How much would you get?
3.
3 kan? How do you represent this in a 4-bit system? 4-bit binary system.
0, 0, 1, 1.
1, 1.
Yes.
Okay. So that is the process of getting to know what is your output based on lookup table punya proses. Multiplication based on lookup table. Okay. So yang ni now saya ambil contoh so that is why dia tak ikut ascending. Biasanya if you want to do this betul-betul, normally what we will do is that kita akan buat 0, 1, 2, 3, 4, 5 sampailah ke 15. Nah 01 ni maksudnya ni lah 00, 01. Sat lagi next stage pula 2, 00, 10. Sat lagi 11 and so on. Okay, ni saya nak cepat dan saya langkau lah sikit ni. Jangan literally, jangan betul-betul ambil just banyak ni faham tu? Maknanya ni kena ada paling kurang 15, 16. You need to have at least 16 lines, 16 rows. Kenapa 16 rows? The first row represent 0. The 16th row represent 15. Okay. So once you get up until this stage, the second phase is actually to derive ataupun to get Boolean expression. How do you get Boolean expression? Is by using Karnaugh map. We are encouraging you to use Karnaugh map. If you don't want to use Karnaugh map, is it wrong? No, it is not wrong. You can still derive the Boolean expression by extracting the Boolean representation of each and every column. Okay, so this one, you need to build Karnaugh map, right? Karnaugh map for P3, satu lagi Karnaugh map juga for P2, P1 and also P0. Okay, how do you determine the size of your Karnaugh map? Is by looking into how many elements yang it has. Okay, looking into this, I have 4 elements. B1, B0, A1, A0, 4 elements. So, bila I have 4 elements, the size should be 16. So, biasanya senang, I would normally put like this, B0, B1, nanti pula akan ada A0 and A1. Then, the next step is looking into P3. Look at column P3 ni. Look at column P3. Transfer this element into your Karnaugh map. Okay, how do you know to transfer this? Tengok balik your notes in your digital electronics Karnaugh map ya. Make sure like this one is 0000. So dekat 0000, what is the number? Ataupun what is the binary representation? Kalau kosong, letaklah kosong. Kalau satu, letaklah satu and so on. Build up lah sampai habis. Okay, sampai takat ni okey tak?
Apa nama dia? Karnaugh
map. Okay.
Saya tak ingat.
Tanya
Kita boleh je. Karnaugh.
Karnaugh. Nama pendek dia K-map. You guys can see my screen kan? Okay, nanti boleh pergi Google kat sini. Type Karnaugh map. So dia ada yang 4 variables, ada yang 2 variables, ada yang 1 variable and so on. Okay, saya langkau lah dulu Karnaugh map ni. Sebab you tengok balik you punya digital electronics tu. Sebab kalau tak, saya tak sempat. Kalau ada extra time, saya masuk kepada Karnaugh map tu. Ni ya. Okay, elemen dalam Karnaugh map ni can be X, can be 1, can be 0 and so on. Okay? Boleh? Selain
Boleh.
Allah. Sangat besar. Okay, other than that, any other question relating to relating to the second stage? Bukan the second stage, the second way of doing it. Okay, the first way tadi kita transfer macam ni So the second way of doing it is using Karnaugh map. Okay, the third way of using it is by using multiplexer. Ingat lagi tak benda ni? Okay, siapa ingat benda ni? Balik kampus saya bagi coklat. Ataupun huduh sangat gambar. Bagi tak recall. If you see this symbol, you know it is an N kan? If you see this trapezium symbol, what does normally trapezium represent?
Multiplexer.
Thank you. Ada orang ingat juga. Thank you. So multiplexer, how many elements are there in a multiplexer? There should be input lagi. Output and select. Okay. Another way of representing your circuit can be also saya buat balik ayat. Another way to execute ataupun to implement your digital circuit is by using multiplexer. So in a multiplexer, you have like this ya. You have element for input, you have element for output, and you have element for select. Select and input are input. means there are elements that you feed into your multiplexer. Lawan kepada multiplexer is demultiplexer. So select and inputs are the elements that you feed to your multiplexer. And outputs are the element of output that you have. So let's take the example that we have just now. You have, in our case just now, A0 and A1. And then we have B0 and B1. So the elements that you want to multiply will become your select. Okay. So in this case, how many bits will my select be? Select will represent the element of A and also will represent the element of B. Currently, my A is 2 bit, means I'm having A0 and A1. Whereby my B is also 2 bit, whereby I would have B0 and B1. Okay. That being said, looking at this, how many bits is my select? How many bits should my select be? 4 bits, 2 bits for A0 and A1, 2 bits for B, B0 and B1. So far until here, okay?
Okay, dah.
Okay.
Yes, ma'am.
When you have 4 bits for select, how many bits will your input be? Anyone remembers rule of thumb for multiplexer? 2 to the power of select is equal to your input. If you have 4 bits, means your input is 16 bit. Okay. Kalau your input is 2, only 2, your input is 2. So, kalau your select is only 2 bit, your input will become 2 to the power of 2 is equal to 4. Okay. Okay. In this case, is 16. So, how can you transfer is by looking into here. Okay, remember tadi when I mentioned when you do truth table, this is actually also a lookup table. Okay, now we are looking, tadi ni what we did is lookup table. Truth table ni masuk pada cutoff map. The same table, we are referring to the same table. We look at this point, 0, 0, 0, 0. What is your P3? 0. So here, how do you implement this one? Multiplexer for P3 for 0, 0, 0, 0. This is 0. You will have here up until 16 input. Okay. For 16 pula. 16 means 1, 1, 1, 1. When you have 1, 1, 1, 1, dia equals to 3 by 3 kan? 3 multiplied by 3 equals to 9. Bila 9, this is equals to 1, 0, 0, 1. So for P tadi, if 3 multiplied by 3 is equals to 9 and P3 is 1. So at multiplexer of 16 yang ada dekat sini ni, you can put here as 1. So dekat sini there will be combination lah. Okay, if this one 0, 0, 0, 1. 0 multiplied by 1. So this should be 1. 1 pula, minta maaf, kosong. 0, 0, 0, 0. 1, 2, 3, 4, 5. Okay. Ni, when you want to derive the ni one, this is A0, A1. This is B0, B1. Okay. When you want to derive the output tadi ni, the one that we seen here just now. So this one kan, when you divide this into 2, as if you are multiplying. Kosong multiply by kosong. So you dapat kosong. Kosong multiply by 1, still kosong. Kosong multiply by 2, still kosong. Okay. At the third row ni, it is kosong multiply by 3 is also kosong. 4, 1 multiply by kosong pun kosong. Okay. Tapi when it comes to 5, 1 multiply by 1, what is the result? 1, isn't it? 1, if you were to represent this one, it will be 0, 0, 0, 1. So still this will become 0 for P3. Tapi untuk P1 nanti, untuk P0, representation of P0, it will become 1 lah. Okay. So this is another way of implementing it by using multiplexer, whereby instead of feeding your cutoff map the element that you feed your Karnaugh map ni, for P3 kan, the element that you feed your Karnaugh map, that can be the input for your 4-bit multiplexer. Okay, so when let's say you have an execution of B2 multiplied by 2 multiplied by 1, for example. So for B2, 2 multiply with 1, B is 0, 1, 0, A is 0, 1. 2 multiplied by 1, it should result as 1, as 2, sorry, 1, 0. So your P3, your P2, P1 and P0 later will have this combination. Will have these results. Okay, this is another way of implementing this circuit by using multiplexer. I am not so sure whether I get you more confused or not. May I get a little feedback here? For implementation using gate, are you guys okay? Gate maksudnya yang ni tadi. Implementation using this concept, are you guys okay?
Okay, madam.
Okay. Siapa yang okay, can you raise your hand? Okay. 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 In exam, if they did not mention which way of executing it, it is up to you to choose which choice. But if they specifically mention you need to execute it using multiplexer, you have no choice. Okay? Okay, it's okay. Kalau you don't understand pun tak apa. Kalau you understand, you raise your hand. Okay, tak apa. Kalau you don't understand, okay, means I need to explain this more. Okay, number 1. Number 2, are you, can you put your hands down? Raise your hand up if you are okay with second execution, implementing the circuit using gates, using Karnaugh map. Raise your hand if you understand. If you don't understand, it's okay. You can lower your hand. Using second method, yeah, which is transfer it into Karnaugh map, and from Karnaugh map to you get your expression, and from the expression baru you draw the circuit. Numbers of raised hand 9. Okay. Okay, thank you. The last one before we dismiss today. Can you please put your hand down and raise your hand if you could understand how can you implement this circuit into multiplexer? If you know how to implement this into multiplexer, can you raise your hand? No. Okay, alright. It's okay. So that being said, I'm going to dismiss the class now. Next class, I won't continue with ALU yet. I will cover this multiplexer because this would be the baseline ataupun this would have, I mean, it is good. It is a must for you to understand on how to translate this into multiplexer because then you can see how ALU is being implemented. So let's end up at this stage first. I will share this recording later. And I am thinking of having a class maybe on Saturday or Sunday. I will discuss this in our group later. And it's okay if you have other commitment. I will adopt the same way as well. I will record and I will share with you later. Okay? So that's all for today. I am dismissing the class now.